All right. Our 4-methyl hex-1-ene with hydrobromic acid. All right, so this chirality center it's saying is R. And as long as the priorities don't change, since the reaction doesn't occur there, it's going to stay R at the end, but we'll get there in a minute. So your first step is to list and label everything, figure out your most reactive feature is the pi bond. And so that's driving the reaction, and so we're going to base everything else off of that. Because the pi bond is what's going to react, it's helpful to know which carbon is going to become the incomplete valence shell atom. Also, so it's good to label those. When the bond opens up, that's telling you that you're going to have the carbocation on the secondary carbon. This is going to react with an electron deficient atom, so that would be the hydrogen. Very good. So now there's the hydrogen. At this stage now, since you have an incomplete valence shell, the additional feature is that you're going to see if a shift occurs or not. One thing that could help you avoid missing the possibility of a shift would be to label the types of carbons. And since you have a secondary next door and a primary, then that's not going to have any shifts. So then the last stage is you got to take care of this incomplete valence shell because that's such a reactive issue. So list and label all of your reactants. You can include anything from above that didn't react or that was created as a result of a reaction. So since everything up here reacted, we're not going to list that again because we've kind of used up some of it, but you did create the bromide when that bond broke. So those are your major features. You're looking for non-bond electron pairs present in the highest concentration that could form the fourth bond, so that adds on there. And then at the end, you check it to see if you've created a chirality center or two as a result of the reaction. You did create a chirality center here. Since this is trigonal planar, it means the bromide could have added above or below. That means that you have both possibilities of R and S. This chirality center didn't change. The only time that you would change the designation for it would be if the priorities of the groups changed, but it didn't because this had hydrogen as the fourth priority. This was the first. This is second. That's third. This is still your number one priority, 2 and 3, so therefore it didn't change anything, so it's still labeled R. Any questions about that? You still have a pi bond as your most significant feature. You have several things that have partial positive charges that you could react with, but the methanol, these bonds are too strong, so you're not even considering those. Your best choice is the hydrogen on the methanol, acidic methanol. When the bond opens up, you have a choice between primary and secondary. It goes on the secondary. The electrons go from the pi bond to the hydrogen, and when the bond breaks, they go towards the oxygen. Form positive, break negative. Once you've got this, then you decide if a shift occurs. You can shift over to a tertiary carbon. That means since this is tertiary, it means you're going to do a hydride shift. The only time that you would consider doing a methyl shift is if this is a 4 or you have angle strain in a ring. Otherwise, your resource is the hydrogen. You want to keep as many carbons on this as you possibly can because that's what's stabilizing it. So you move the hydride over a notch, and that puts the carbocation here now instead. That's still a very reactive molecule. So that means you're not done. List and label all of your resources and figure out what electron pair is going to add on here so you can have a fourth bond. We've taken the hydrogen off of the acidic methanol, and besides that, you wouldn't use this non-bonded electron pair to form a bond. That would create a 2+ formal charge on the oxygen. Besides, you're looking at the highest concentration because that's most likely to run into this. This is so highly reactive, it really doesn't care. So go with concentration at this step. The electron pair adds on there, it drags everything with it, and then you can have the hydrogen come off. This doesn't have any newly created chirality centers, so there's nothing to say as far as R and S for that one. Any questions? All right, I kept hearing about cyclic stuff makes you mental. Yeah? Okay. Maybe if you translate that into numbers, like over here kind of thing, maybe it won't look so imposing to you. And anytime you're looking at a carbon, you're just counting how many carbons it's directly attached to. So for instance, that's a tertiary carbon, that's a tertiary carbon, these are secondaries. You have electron-rich pi bond. That's going to open up and react with something electron deficient, which is the hydrogen again. The hydrogen can only have one bond, so it has to let go of the bond to bromide. You're forming towards the positive, breaking towards the negative. There you go. After you've shown how it reacts and you draw this out with a carbocation, watch for a shift. This is a tertiary carbocation because that carbon has 1, 2, 3 bonds to carbons. You're not going to shift when you have a tertiary carbon because you're not going to ever be able to do any better than that. But if you wanted practice with writing out the numbers, this one is 1, 2, 3. This one has 1, 2. So just, if you fill in the numbers, maybe you'll be able to see that you wouldn't do a shift or whatever. Because this is an incomplete valence shell, it's very reactive, so it's not going to stay like that. So list and label all of the resources that you have. We're going to say that since that was involved in the reaction, we're not going to use the H bar. We're going to take the bromide down here, and that has the non-bond electron pair you'd want. So you add that on. When the bromide comes on, you're going to create a new chirality center here because this carbon has a methyl group, a bromo group, a carbon with a methyl group, and a CH2. That's 4 different things attached there. So because that's a chirality center, and then this is also a chirality center, carbon, hydrogen, a CH2, a carbon with a methyl and a bromine attached to it. This is trigonal planar, so the hydrogen could have added to either side here. So this one would be R and S. The carbocation is trigonal planar, so the bromide could have added to either side. So this one is R and S. So you'd have the 4 possibilities. Or if you wanted to draw it out, you could have both of them going up, both of them going down, one up, one down, the other up, the other down, if you're feeling ambitious. Any questions about cyclic other than that you want more of these because you love these so much?
So as long as you're making an alteration to a chirality center, you count it as R or S.
That's right.
So if there's already a chirality center, but then you alternate it in any way, you then have to label it as R or S.
Yeah, so this wasn't a chirality center, of course, to begin with. So we're not altering a chirality center, but we're creating one. And as long as you're creating one, it's R and S because every step.
Other ones, like where it's already a chirality center, but then you switch out, like let's say a hydrogen for bromide or bromo. We'll just have to label it as R or S. Okay.
So yeah, we're going to run into that type of situation next semester where you're actually reacting with this carbon here. But if for purposes of this semester, you're always going to be creating a trigonal planar chirality or a carbocation, or you're going to start out with a trigonal planar vinylic carbon. And so as long as you had a reaction that involved one of those 2 types of features, it's always R and S mixture. Next chapter, it's not the same, but for now, yes. Reactive pi bond, look for something electron deficient. This also would have water present at a high concentration, but you're crossing off the hydrogens from the water. When this opens up, you have a secondary carbon or a secondary carbon to put the carbocation, but this one is a little bit better because it's a secondary with an option for a shift. So that's going to create a more stable carbocation after the shift when you have the tertiary there. So we're going to go with this one right here. You open the bond up, you have the carbocation. Now if you label, you got secondary, secondary, quaternary. So this one, your only option is to move a carbon over because you don't have a hydrogen since it's quaternary. So if you move that over a notch, there's that methyl group there, and then the carbocation is here on a tertiary. We're only going to do one shift for any given reaction because chances are that it's going to find whatever's going to form the fourth bond before it can keep shifting, so only ever consider one shift. Anyway, you got the tertiary. This is an incomplete valence shell. That is still a crisis, so you're looking for something with non-bond electron pair. Since the stuff left over from up here, water is going to be present in a high concentration. And so that's why you're going to consider that, because we're going to use the non-bond electron pairs, not the hydrogens, so it doesn't matter that the hydrogens are crossed off. When that adds on, you can let go of a hydrogen to create an OH group there. This created two chirality centers, one here and one here. Since this one was created from a trigonoplanar carbocation, so when the methyl group moved over, it could add to either side. And then you had a carbocation here that the water could have added to either side. Each one of them would be R and S mixtures for the molecules in solution. Any questions, issues, weak spots, problems? Yes.
I get a little confused when, I don't know why, but I start CH3 get CH2 instead of CH. I don't know all the amount of...
Right here?
Yeah, I can show you this. So when I write it down, I know what it is. I start first at CH3, CH2, 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 then CH3. But then when I looked here, they did not see CH.
Yeah, so this is just once again where you're counting the number of bonds. For instance, here you have 1, 2, 3 bonds, and so that means you only have one hydrogen to make up 4. You're always just counting to 4. Unless you have a carbocation, in which case there's only 3 bonds. Yeah. Yes, ma'am. Just a minute. What?
So you were saying to use this one instead of this one on there, so when I'm doing it, it looks like this. And then after that, this would be the carbocation?
No, so the reason why we don't want to have the carbocation there necessarily is because that's secondary. This one would be a secondary carbocation too if you put the hydrogen over here, but then you could do a methyl shift and that would make it tertiary.
So I am putting it on this one, not this one.
The carbocation goes here.
Yeah.
And so that means the hydrogen is there. Yeah, so you're always worrying about where the carbocation goes, not necessarily where the hydrogen goes. That's just kind of a repercussions of it, I guess. Okay. All right. So you went through E. 6, 7, 8. There are 8 left, but that's okay because you have 2 days to do it. So finish it up and for your homework for Wednesday. That's how much I love you. Finish up 13. And I'll show you, though, how to do reactions with peroxides so that you can do those. You're clear on the homework? All right. I'll work through this with you. So peroxide. So I'm on page 32, and I'm going to show you using an example from the guided practice how to work with peroxides. We went over this in chapter 5, but we haven't used it a lot, and so you haven't seen how to apply it. So if it feels foreign to you, it's okay. We'll work through this. So I'm going to show you the purpose of the peroxide, why it creates a bromine radical, and all of that, all the steps involved in that. But if that makes your head hurt, just remember that the peroxide is used to create a bromine radical, and that will be your start point. But it's best if you can kind of understand where it came from in the first place, too. So off to the side here, I've got peroxide drawn out. Remember, we talked in chapter 5 about how peroxide is sold in brown bottles in the pharmacy because it's very sensitive to anything like light. And that's because the oxygen-oxygen bond is very weak and it breaks very easily. That's the whole point to having peroxide. The reason why it breaks easily is because oxygen is very electronegative. It's the second most electronegative atom on the periodic chart. And it's also small because it only has 2 shells. So you're putting 2 atoms right next to each other that have quite intense negative charge to them, and that's repelling. So they want to pull apart. And when they do rip apart, it's going to rip the bond evenly because neither oxygen is more electronegative than the other. So that's why I'm diagramming this out as it just splits. So 1 electron goes on each oxygen. That means that you create 2 hydroxide radicals. But that's why this is such a good disinfectant. You've got all these radicals that can kill things and stuff. Anyway. The major issue with radicals is that they create new radicals when they react because they only need 1 electron, so they're only going to steal 1 electron from some other poor atom or bond, and it's going to leave something else with an unpaired electron. So unlike carbocations, where the only factor you're looking at is how high is the concentration and does it have a non-bond electron pair, and that's about all you go by. Here you have an additional thing that you have to take in consideration, the fact that you're creating a new unstable product. And so in addition to things like concentration, you're also looking at factors like how strong is the bond that would need to break to create the new radical, and how stable is the new radical that you're forming. Sorry to go back, but I just want to remind you, is it in this chapter? No, it's in chapter 5. Duh, I remember now. I'll go back to chapter 5 because it's going to ring a bell for you, I hope. 30, 31, 32. We had an exercise in chapter 5 when I was introducing the concept of peroxide and radicals where I said you're going to base your considerations on the stability of the new radical that is going to be formed since that's so unstable. And then we talked about how the larger the atom is, the more stable it is as a radical. And then you also have factors like resonance that will come up later. But then we went through and said, okay, which one is the more stable radical in each pair? And it was like bromine, 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 because it's like that's the biggest atom in each case, except for D. So, coming back to here, when you're thinking about how to react this hydroxide radical, then your resources for reacting with it is the HBr and the 3,3-dimethylpent-1e. The one that's going to make the best radical, though, is the bromine. So we're going to react that with the hydrobromic acid to create the new bromine radical. Another thing that I want to draw out for you just so that you can picture.
Why does it kill you when you drink it then?
Well, it depends on how much you drink. It doesn't necessarily kill you, but it creates a lot of radicals.
Just starts reacting with like your stomach.
And once radicals react, they grab electrons from anything. So, for instance, that can damage DNA or cell membranes or whatever.
Do you think your stomach acid?
Probably not the acid itself. It probably just affects the cells in the stomach lining. So if you're going to steal an electron, you got two choices. You could take it from a non-bonded electron from the bromine, which normally would be where you'd want to go, right? Because those are only held by one nucleus, not two. And so that would be kind of a nice place to steal an electron. But if you do that, so you have this, then not only is bromine a radical, because it has an unpaired electron, but if you split this bond and count the number of electrons around it, it also has a +1 formal charge. You have a radical and a +1 formal charge. Yay! Yeah, that's not going to happen. So instead, what we want to do is steal an electron from the bond so that the other electron goes on the bromine to create the bromine radical. If you do that, then it's just a radical. You don't have the formal charge associated with it. Okay, so that's what we're going to do, and that's what I have diagrammed out here. I'm taking one electron from the bond along with the hydrogen to put it on here, and that will make water. And then you're going to have the other electron go onto the bromine to create the bromine radical. So as I said, if this makes your head hurt, splitting this and then stripping a hydrogen off of HBr to create the bromine radical, at least know that that's the purpose of the peroxide, is to create radicals so you get a radical mechanism going, and it will start by creating a bromine radical because that's the most stable. Also a note of caution though, notice that you're using trace amounts of peroxide. That's because once you get a radical mechanism going, it creates a new radical, and that radical will create a new radical, and so it just keeps going on its own. So you just need a little teeny bit to kickstart it. So what that means is we're not going to be listing the peroxide anymore in the list of reactants because we split it apart anyway. We're not listing the hydroxide radical because it's present in such a small amount. And we're also not going to list the water because it's only a trace amount of water. So it's not the same thing as when you had water as a solvent. Okay, so all of those potential reactants are gone. They're off the table. All we have left is the alkene, the bromine radical, and we're still going to have hydrobromic acid that hasn't reacted because we only put in a trace amount of peroxide, so we've only used up a trace amount of the HBr. So those are going to be the list of reactants from here on out. All right, from here on out, it's going to react kind of similar to what you've seen before. So you're only going to use, okay, the bromine radical is the most desperate atom in the solution right now. That's the most reactive reactant, so that's what's driving the reaction. You need to find a source of electrons for the bromine radical. You could take another molecule of HBr and then form a new molecule of HBr in a bromine radical, but that's not doing any good. So we're going to instead consider any reaction that you could have with the carbon and the pi bonds. Since the pi bond is electron rich and fairly reactive, it means that that's going to be able to, the bromine's going to be able to strip one of those electrons. When it does, you're only going to use one of the two electrons in the bond, and that means that the second electron is going to go on the better carbon that could handle the radical. So just like before, you want to label these as primary, secondary, or tertiary. That tells you where the radical ends up, and that's the only major criteria since that's the source of instability. And I said it strips the electron. That's not quite right. It's going to use the electron to form a bond. So I've shown the reaction and the labeling both in that one step. And I'm off a step here. Okay, so since I moved the one, or had the one electron left over, that's on this carbon. And then the other electron paired up with the one electron from bromine to form a new bond. Radical always creates a new radical. Unless you have two radicals react with each other, but I digress. So now step 3 is look to see if you have a shift. Do you have any potential for a shift here? No, because it's a radical, so it doesn't have room to accept both electrons from a bond moving over. So I drew it like this so that you'd be tempted. I was trying to get you to take the bait, but no, it's you're not going to be able to do anything with that. Because it's a radical, it means that you have an incomplete valence shell. And if you have an incomplete valence shell, there, then you're not going to just leave it like that. It's still too reactive. So you want to list and label all of the potential reactants that you have. Okay, so that's obviously one of them. Going down your checklist, concentration's too small, too small, too small, or I'm sorry, too small. The bromine radical is small. You have water, that's too small. The only thing that you have present in a fairly good concentration is the hydrobromic acid that didn't react with the peroxide radical in the first place. Remember, we're looking at stability and probability. The carbon radical only needs one electron. You're going to create a new radical. The new radical you'll create is the bromine, because that's more stable. So just like before, we're going to take one electron from the bond with the hydrogen to form the new bond and create a bromine radical that now can go back and find a different alkene to react with, and that's why I say it's kind of cyclic. So your final product will be that. And now, just like before, your last step is figure out what the stereochemistry is. Since a radical is trigonal planar, same as a carbocation, it means that you'll have R and S at any carbon where that was a factor. So this is a new no, that isn't. You don't have any chirality centers. You're done. But if you did have a chirality center, it would be R and S at each one that was created. All right, give it a try.